Let us start this lecture with a thought process. As the magnitude of molecule determines the character of a compound, the magnitude of the humanity determines the character of a human being. So, it is a very important statement. Like we can see that molecules really decides the character of a compound. Similarly, the humanity is very important for a animal man to become a man. So, that is the objective of all the education what we impart or what. So, in the last lecture we discussed about various governing equations for analyzing the rocket engines and particularly thermodynamic aspects of the rocket engines can be analyzed by using those governing equations. And today we will be discussing about the chemical reaction, because of fact that there will be a reaction between the fuel and oxidizer of the propellant, and it will be releasing heat. As a result, there will be a lot of chemical products will be formed. Now, we need to see and understand how we can really analyze it, and for that we will be discussing certain things which are already known to you. Let us say that 1 mole of methane is reacting with 1 mole of oxygen going to the product of certain moles of water and the carbon dioxide. Of course, certain amount of heat will be released. This is basically heat release. And that is the objective of this reaction, that it should be endothermic in nature, because we need to produce some heat. Of course, there are some reactions which are endothermic in nature, but the chemical reaction must be exothermic such that it can be utilized in the combustion process, or it will be released during the combustion process. So, therefore, is it question arises balance? Of course, certainly no, but a question arises, what do you mean by balance? Basically, what you will be doing, you can do a mole balance or a element balance, right, which is the right one. Definitely it will be the element balance which is the give the right result. So, balance equation would be, that is 1 mole of methane is reacting with 2 moles of oxygen, giving rise to 2 moles of water and 1 moles of carbon dioxide. Keep in mind that this is a representative of the reaction. Actual reaction need not to be taking place in the manner what is written here. So, whether it is balanced or not, how we will know? For example, if you look at this is 1 mole of methane means is a 16 grams of methane is reacting with 64 grams of oxygen, and it is giving rise to the product 36 grams of water and 44 grams of carbon dioxide. If you look at left hand side, it is basically 80 grams total together, 64 plus 16, that is 80 grams, and the right hand side is also the 80 grams. That means the mass is conserved during this reaction. In other words, the 80 grams of the methane and oxygen together is going to produce 80 grams of course, water and carbon dioxide total. That means mass is conserved in this case. So, no mass is created or destroyed in a chemical reaction, only changes in their forms take place, that we can infer for this observation. Keep in mind that that is not true, particularly when the amount of heat release is very high, like in nuclear reaction. mass is converted into energy, as we know. So, therefore, it is because the amount of heat released during the combustion is very small, therefore, we can say very safely that no mass is created destroyed in a chemical reaction. However, we will be using the air and also we may be using different oxidizer, but to as we use air for most of the combustion, not in rocket propulsion, but in general combustion. So, therefore, let us look at this. 1 mole of methane is reacting with 2 moles of air. Here we are considering that air consists of 79% of nitrogen and 21% of oxygen only, and then it is giving product of 1 moles of carbon dioxide and 2 moles of water and 7.52 moles of nitrogen, right. So, therefore, it is the balanced one. What is stoichiometric? That if you recall that it is the ratio of oxidizer and fuel which is sufficient to burn the fuel completely, leading to the formation of products, complete products of combustion. So, of course, this is the theoretical oxidizer fuel ratio which is must be given, but in reality you need to give more amount of oxidizer per unit fuel to have a complete combustion. So, let us look at 1 moles of CX and HY. This is basically a generic hydrocarbon. For example, methane, if it is methane, this will be X will be 1 and Y will be 4, that is CH4, and similarly if it is propane, this is C3, X is 3 and Y is 8. So, this it can be represented very well, and it is 1 mole of this generic hydrocarbon is reacting with A moles of air and giving rise to the X moles of carbon dioxide and Y by 2 moles of water and 3.76 A moles of nitrogen. So, if you look at this is well balanced. So, therefore, you can also calculate from this that A is equal to X plus Y by 4, and then air by fuel stoichiometric will be mass of oxidizer or mass of air divided by mass of fuel, which is nothing but your 4.76. This is 3.76 and this is 1. So, that is 4.76 A, and this is by of course mole, this is by mole, and then you will have to multiply it by the molecular weight of air and divide by the molecular weight of fuel. This MW is basically molecular weight. And this is a formula what you can keep in mind for particularly air. For methane air fuel stoichiometric ratio is 17.11, while for other hydrocarbons except methane, so air fuel air stoichiometry will be around 15. So, that a number, rough number, it is not exactly 15, it may be 15.3, it may be 15.2, it may be 15.5 for different, but this is a ballpark number you should keep in mind, that is for other hydrocarbons, for all the hydrocarbons other than the methane air. So, equivalence ratio we need to define, because this is basically non-normalized air fuel ratio and air fuel ratio stoichiometric divided by actual air fuel ratio, and you can also put it other variant fuel air ratio divided by fuel air stoichiometric. If phi is equal to 1, what is the meaning of that? That is basically it is stoichiometric, right. If phi is less than 1, implies that this is fuel lean mixture. If phi is greater than 1, this is basically implies fuel rich mixture. And you can find out also percentage of stoichiometric air. This is nothing but 100 divided by phi into that is the percentage, right, what you will be having. And when we are dealing with various combustion products, and it will be containing lot of spaces, therefore, we will have to learn how to deal with mixture. And as I told earlier that we will be considering this fluid to be behaving as an ideal gas in rocket engines, because of fact that temperature is very high and the pressure is moderate, it is not very high. If it is very high, we cannot really apply. We will be using mostly the ideal gas law for analyzing this problem because of its simplicity, and also it is very elegant. The question is, what are the methods used to specify composition of a mixture? And all of you know that these things what we will be discussing, and there are two methods. One is mass analysis, other is molar analysis. That means one will be dealing with considering the mass of the species, and also the another I will be dealing with molar of the species. And when we are dealing with mass of the species for individual species for dealing with a mixture, then we will have to use also the mass fraction. So, the mass analysis of a mixture of ideal gases can be considering the fact that the mass is conserved. That means, total mass of mixture mm is equal to the sum of masses of constituent gases. For example, if the combustion gas contains fuel, or let us say methane, and oxidizer, carbon dioxide, and water, let us say this only 4 species is containing, then naturally the total mass will be mass of individual species of these gases like methane, oxygen, carbon dioxide, and water. That means, the total mass of the mixture mm can be expressed as the sum of the masses of the constituent gases of like, for example, mm will be Ma, because this mixture containing A gases A, B, C like N. So, mm is equal to Ma plus Mb plus Mc plus up to the nth species of the mixtures, right. And this can be written as summation of m dot I, and I is equal to 1 to n. It may be 10, it may be 5, it may be several number, whatever it can be. So, if I will divide this equation by mm, what I will get? So, this is basically equal to 1, and this we call it as basically the mass fraction, right. This is we call it as a mass fraction, and mass fraction we can define as xi is your mass fraction. So, this will be become A. Similarly, this will be xb, and similarly this is xc, and this is your xn. So, this equation becomes basically 1 is equal to xa plus xb plus xc plus plus xn, that is summation of xi when I is equal to 1 to n. So, this is the expression what it says, the sum total of mass fraction of constituent species is equal to 1. So, this you should keep in mind, and that is basically is important one to keep in mind. So, let us look at that is the mole analysis. Similarly, total number of moles in a mixture is equal to the sum of number of moles of each constituent of the mixture, that can be expressed as Nm is equal to Na plus Nb plus Nc goes to the Nn, and this, if you divide this Nm, then you will get this expression, and this is Na by Nm is nothing but your basically Ya, that is your mole fraction. So, and similarly you can write down, express this thing as 1 is equal to Ya plus Yb plus Yc, and goes to the goes on till plus Yn, and keep in mind that the sum of mole fraction of individual species of a mixture is equal to 1. Now, but we know that mass Mi can be related to Ni, that is the mole of n mole of Is species with the molecular weight of Is species, as Mi is equal to Ni Mwi. So, we can use this expression in the above. Then we can write down that M is equal to, we know this expression Ma, and in place of Ma, this is nothing but your Ma is equal to Na and Mwa. Similarly, this is your Mb, and goes on till the summations, right. This is also Mn. So, you can see that this is coming over, that means you are expressing the mass in terms of mole through the molecular weight. Then if I divide this expression by the Nm, and then I will find that this is nothing but your, this is mole fraction of A species, and this is mole fraction of B species, and this is mole fraction of N species. In place of Mm, I can write down this as Nm Mwm. So, Nm will cancel it out. So, I will get molecular weight of mixture is equal to Ya Mwa plus Yb Mwb plus till this is Yn Mwn. So, this is the way to find out molecular weight of the mixture, because it is important to find out this, and provided we know the mole fraction of each species and also respective molecular weight. And we know this is mass fraction of Is species is equal to Mi divided by Mm, which can be said that Ni and M, and this is nothing but your the mole fraction of Is species Yi, and we can relate basically Xi in terms of Yi and molecular weight of Is species and mixture. So, if I know this molecular weight of mixtures, and if I know this molecular to Is species and mole fraction of Is, I can find out very easily the mass fraction of the Is species, or vice versa. If I know other one, I can find out. That means by this we can basically calculate the mole fractions if I know the mass fractions and vice versa. Now look at the heat of reaction and formation, which we will be using finding out how much heat being released during the chemical reactions. And if I consider a burner or a combustors where the 1 mole of methane is entering with the 2 moles of oxygen and reacting over in this volume, this is your Cv, and this is your combustion chamber, and it is giving rise to the product certain moles of carbon dioxide and water. And keep in mind that it is entering at 25 degrees Celsius and 0.1 megapascal in this example, and it is also leaving at the same temperature and same pressure, and certain amount of heat which will be released here you can really find out, that is Q. And this we need to invoke the first law of thermodynamics for this control volume system, and we know that work done is 0 here, right. Shaft work is 0 and is a steady process, and change in kinetic energy is 0, change in potential energy is equal to 0. So, therefore, with under this condition we can get that Q is equal to dH, that is change in enthalpy, is nothing but the amount of heat being released, and that is Hp, that is the total enthalpy of the product minus total enthalpy of reactant, is equal to summation of Ip Hip minus the NIR and HIR and its sum, that means summation of NIR HIR. And keep in mind that as this temperature and pressure is same and the change in enthalpy, what we call as the heat of reaction, and this Hip is nothing but your enthalpy of formation per unit mole of ith reactant, and Hip is the enthalpy formation of per unit mole of ith product. So, if I know these values of the heat of formation per each species and know the mole fraction, I can find out the heat of reaction very easily. And this heat of formation at standard temperature and pressure are generally given in tabular form for each species, and using that we can do. And let us look at what is the meaning of this heat of reactions, and keep in mind that this is the heat of the total enthalpy of the reactant, this is the enthalpy of product, and when we are evaluating at as basically at 298 Kelvin, the difference if you look at it is basically is that we call it as a heat of reaction, and this negative. Keep in mind that this I have drawn as a parallel line, but need not to be, as I am seeing this for a smaller range, therefore, it will be like that, but however it will be diverging. Keep in mind that if this heat of release is being utilized, and then you can get a higher temperature, that is the adiabatic temperature. This is adiabatic temperature, and this happens to be the negative if you look at heat of reactions, particularly for exothermic reaction. So, this is being utilized for the heating of the combustion product, and that high temperature and pressure gas is expanded through a nozzle for getting the thrust. So, as I was telling that heat of formation of certain important species I have shown here in this table, which is at 25 degree Celsius and 0.1 megapascals. You can see that for stable species like oxygen, it will be heat of formation will be 0, and similarly for hydrogen at it will be 0, whereas for hydroxyl and other thing it will be positive values, the heat of 42.3 kilojoule per mole, whereas the water when it is gas it is minus 242 kilojoule per mole, and water when it is liquid this is minus 286 kilojoule per mole, and this difference is basically due to the heat of vaporization. And keep in mind that we will be using this carbon dioxide gas 394 kilojoule per mole, and various methane, propane, butanes are given, and so also the kerosenes which are given here, and keep in mind that kerosene is basically mixture of several components. So, it is represented as CH1.842, but it may be different also for different kind of kerosenes. So, these kind of tables will be available in the some data book or in the some combustion book. You will have to utilize that for calculating this thing. So, let us look at 1 mole of methane is reacting with oxygen in a stoichiometric ratio. Consider that the reactants are temperature of 298.15 Kelvin and pressure is 101325 pascals, and we need to find out the heat of combustion. So, stoichiometric reaction is we can find out because that is given. So, that will be the 1 mole of methane which is in the gas form reacting with 2 moles of oxygen which is also in gas form, giving to the product 1 mole of carbon dioxide and 2 moles of water. Both carbon dioxide and water also in gas form, gaseous form. So, therefore, you will find out basically it is a balance equations, you can see yourself. The heat of reaction will be n moles of carbon dioxide into heat of formation of carbon dioxide plus n moles of water and heat of formation of water minus this is n moles of methane, heat of formation of methane plus n moles of oxygen, heat of formation of oxygen. If you look at in this case, this is basically n is 2 and CH4 is 1 mole and water is 2 moles and the carbon dioxide is 1 mole. So, now it is known, but in real situation it is known, and once you know this thing and you get this respective heat of formation from the table what I had shown you earlier, and you will find out this heat of formation for carbon dioxide is 394 kilojoule per mole, and this is this one, and this is the heat of formations. Keep in mind that this water we have taken in the gaseous form. Had it been in the liquid form, it could have been different values. So, that you will have to one has to be careful of while dealing with that. And of course, the oxygen heat of formation is for oxygen 0 and methane we have taken here. So, when you substitute these values, you will get this is something 803.5 kilojoule amount of heat being released for burning 1 mole of methane. And when you say that heat of combustion is basically heat of reaction, and this is a negative value because it is an exothermic reactions, and we say the mod of this exothermic reaction divided by mass of the fuel, and we will get something 50.2 megajoule per kg of methane. Keep in mind that heat of combustion it can be in terms of joule per kg or it can be joule per mole of the methane. So, that it being used. So, therefore, we have learnt all these things, and we will stop over here. In the next lecture, we will be discussing about how to calculate the adiabatic flame temperature. Thank you.